Good afternoon. My name is Murad. I am from Uzbekistan. I am a researcher at Urgench State University. My topic is influence of laser plasma parameters on the formation of nanoscale structure on metal surface. Introduction. Laser-induced periodic surface structure, LIPSS, or periodic structure, were first discovered by Birnbaum in 1965 by ablation of semiconductors with a ruby laser. In 1983, Canadian scientists G.E. Spey and Jeff Young first developed the ellipsis theory based on the Fourier component. In recent years, the interest of scientists in this field is increasing. We can see an increase in the number of articles on ellipses in the Web of Science database. Very authoritative journals are located. See figure. Here in the number is the number of the lecture created in the period from 2000 to August 2023. This work investigates the effect of laser plasma parameters on the formation of nanostructure on the surface of metals. We analyze the plasma emission spectra by calculating the electron density and temperature at conditions that correspond to the formation of laser-induced periodic surface structure and nanospike on the surface of the metals. Experimental arrangements. We used a fiber-based high repetition rate femtosecond laser with a central wavelength of lambda equation 1030 nanometer to ablate the surface of different nickel and titanium. We used chemically available scanning head to scan the laser beam over the target surface. The plasma emission was recorded using high resolution fiber optical spectrometer, ocean optics. The morphology on nanostructure surface was analyzed using scanning electron microscopy. Stack broadening method. The electron density was measured using stack broadening method. After plotting the fall was at half maximum was found and used for further calculation of the electron density in the plasma plum excited during the formation of the different shapes of the ellipses. To estimate the electron density, we used the following equation. Determinant of the temperature. In the first approach, the temperature of the plasma is determined by laser power density. The expression for determining the temperature is as follows. We used different scanning speeds and analyzed the sample by SEM to find an optimum speed to form regular ellipses without creating craters on the ablated surface. Figure represents the same image of the modified surface at 50 and 500 mm/second scanning speeds of the laser pulses. In the case of the low scanning speeds, deposition of nano and micro-sized particles according of the surface nickel, forming a low spatial frequency with 1 pulse minus 0.1 micrometer periodicity, figure A. In the meantime, we observed the formation of the high spatial frequency at low scanning speed, figure B. In the case of titanium nanospikes were observed at the low 50 mm/second scanning speeds of the ablation pulses. Figure C. The nanospikes have a diameter ranging from 500 to 1000 nanometer and are up to 500 nanometer height. Here we also present the illustration of the diffraction of the light on the modified surface with regular ellipses. See figure E. Optical emission spectra of the plasma created on the surface nickel target. A optical emission spectra of nickel target ablated by 1030 nanometer, 40 femtosecond pulses at the 50 kHz repetition rate. We analyze spectral lines on the ionic transition for the calculation of the plasma parameters. In the case of the nickel, the plasma lines were indefinite using database from NIST. From this database, we obtained that the line of nickel at the 361.9 nanometer corresponds to the single charged nickel ions. See figure E, B, C. Optical emission spectra of the plasma induced of the surface titanium. The steric Broding profile strong T2 ion line at the 376.1 nanometer used for measuring the electron density. Table shows the calculated values of the electron density and temperature for the titanium 2 ions respectively. Ellipsis structure for low spatial frequency periodicity L of the replace is closer to the wavelength L equal lambda of the laser pulses, while high spatial frequency have period significantly smaller than the wavelength L less than lambda. Of case, both categories of the ellipses and be generated during the interaction of the laser pulses with surface of samples. The frequency of the plasmonic wave varies with the electron density according to, hence by controlling the plasmonic frequency, it is possible to control wavelength surface plasmonic polarity. Constellation. HCFL and nanospike structure on the surface nickel and titanium targets vary format at different laser speeds. The parameters of the induced plasma plumb were estimated for regular ellipses and nanospike of the surface of the titanium target at relatively low concentration of free electrons in the plasma of titanium target. Nanospikes formation was observed. The increase in the concentration of free electron density at low scanning speeds of the ablating laser pulse led the formation of HCFL with periodicity LLCFL 0.5 pulse 0.1 micrometer on the surface of nickel. Our findings provide insight into controlling ellipsis structure toward new application and functionalization of materials using ultrafast lasers